let's talk about reading binary phase diagrams. Now, this is in no means intended to replace what we covered in lecture, but because we don't have a textbook for this class, I thought that I would give you something that you could review to prepare for the exam. So, binary phase diagrams have two constituents. Those constituents can be elemental constituents. For example, we can talk about copper and nickel and having a system made of copper and nickel atoms. In contrast, we could talk about systems that are complexes. For example, Al2O3, Fe2O3. And we can talk about a combination of those and the phases that exist as we mix those components together. But there's two of them. As we go to 3, go to ternary, and quaternary, etc. Going from 2 to 3, there's a huge increase in complexity. And that's why many of you who go into, for example, ceramics are going to spend a lot of your time working with these complex phase diagrams, mapping out regions of this phase space, and then finding useful properties. Or more importantly, finding means to create microstructures from those properties. So if we have a binary phase diagram, typically we will hold all, at least when we represent it, we're going to hold all of our thermodynamic variables constant, for example, pressure, and only vary one. And the most common is varying temperature, because that's the easiest to work with. So we may have something that looks like this. Temperature on the y-axis, and then the mole fraction of elements on the x-axis. And I'm going to give you just an ideal system of a mixture of A atoms and B atoms, or A and B constituents. So I'm going to put A on the left, B on the right. Therefore, XB is the mole fraction of B. So it's going to range from 0, meaning 100% A, to 1, meaning 100% B on the right. The simplest phase diagram is going to be a phase diagram that looks like this. And you can imagine this type of phase diagram and the two elements that make this type of phase diagram would be having copper on one side and having nickel on the other. They have a phase diagram that looks like this. And when we have that, at high temperatures we have the liquid. At low temperatures we have a phase which is a solid solution of copper and nickel atoms, and we denote phases using, or solid solution phases, using lowercase Greek letters, and we'll use an alpha here. If we have pure copper, then we have, or pure A, we have a melting temperature, and as we go from liquid, it transitions from liquid to solid at a melting temperature. Same thing if you have pure B or pure nickel, you have a melting temperature. However, when we have a mixture of these, instead of going liquid to solid, we have a region which is liquid plus solid. And now the question is, what can we use this map for? How can we read it? So at a given temperature, a given composition, I'm going to call this XB star, just saying it's the one we chose. You can put a plus sign or dagger or whatever you want, but this is the composition we chose. If we mix A and B, or copper and nickel together, and we go up in temperature, at some point we're going to have all liquid. And if we were to look at it under a microscope, marker's not very good, I'm going to change markers. Looking under a microscope, it's just going to be all homogeneous liquid. And we say to ourselves, well, what phases are present? Liquid. How much? 100% of the phase is liquid. We say, what's the composition? Well, the composition, we just read here, which is our XB star. Now, if we take this and we cool it down, and we come down into this region, Well, that region, we can say what exists. And we look at it, and we have various crystals, but all the crystals are alpha because we're in the region of the diagram which is 100% alpha. 100% of the phase fraction is alpha, 0 is liquid. And we say, what's the composition? Well, each of these has the composition XB star. Going into the two-phase region is a little bit different. Let's pick something, say, here. Well, if we're at that point, and we look at it under the microscope, we'll see something that looks like this. A mixture of phases. Some phases are liquid, some phases are solid. The solid phases are alpha, the liquid phases are liquid, L. Now we can ask ourselves, what fraction of this is alpha and what fraction is liquid? And to do that, we're going to use what's called the inverse lever rule. And to do that, we draw a horizontal line. We call it a tie line, and I don't know why we call it a tie line, but that's what all the textbooks call it. I call it a horizontal line. So you draw this horizontal line through the point you're at in the phase diagram. So you've got the temperature and the composition. And you look at where that horizontal line touches the phase boundaries in our diagram. And there we drop a vertical, and I'm going to identify this point as XBL for the left side, and I'm going to identify this side as XBR for the right side. And you can use whatever nomenclature you want. I'm just using left-right to be convenient. Now, to identify the fraction that is solid, and we're going to call that F alpha, the phase fraction that's solid, you take the length which is away from the solid. So here's the solid region. So we're going to take that length, and we're going to divide it by the total length. So that's going to be XB star minus XBL and we're going to divide that by the total length, which is XBR minus XBL. And similarly, erase this, we can say, what is the phase fraction of liquid? And that, you see where the region of liquid is, so we take the inverse, we take the part which is away from the liquid, and divide it by the total length. So that's going to be XBR minus XB star divided by XBR minus XBL. It's noteworthy that FL plus F alpha equals 1, because if you get one of these right, then the shortcut is just to say that FL is equal to 1 minus F alpha. So why is it that it works this way? Well, the reason it works this way is you can imagine the point where we just barely cross from liquid into the two-phase region, right up here. And if we just barely crossed, and we draw our horizontal line, we have a little part here, and we've got a big part here. And at the same time, we know that it was just liquid, and we just had the first little bit of alpha form, right? So here, looking in the microscope, we're going to have liquid, and then we're going to have little little nucleus of alpha forming, not big. And as a result, we know that the little part divided by the total length should tell us the amount of alpha, or the fraction of alpha. So that's how you remember that we're using the inverse lever rule. So we have a way to identify the fraction of alpha and the fraction of liquid. We can now say, what is the composition? And the way that we read the composition is we simply look at where the horizontal lines, where this horizontal line touches the phase boundary. So where our green horizontal line touches the boundary between alpha plus liquid and liquid, that gives us the composition of the liquid, XBLIQ, liquid. And where our horizontal line touches the boundary between all alpha and alpha plus liquid, that gives us XB alpha. And this is the basics of how to quantitatively read a phase diagram, a binary phase diagram. And the same thing holds true if we go to a more complex phase diagram. For example, let's look at a binary eutectic phase diagram. Let's pick binary eutectic, and we have temperature. On the y-axis, our x-axis is going to again be the fraction of B atoms or B constituents. And the way a typical binary eutectic phase diagram looks is this. And labeling the phases, we know at high temperatures we have liquid. We know that when we're over here in mostly A pure, we have an A compound which has some solubility for B atoms. And we'll call that our alpha phase. Over here, where we have pure B, we have a phase which is mostly B, but it has some solubility for A atoms. And we'll call that beta. I know these are really original names that I picked, but so there it goes. And then, as I mentioned in class, anytime that you have two single-phase regions that are near each other, you're going to have a two-phase region which separates them. And the only time that you don't have that is in very special situations where you have what's called congruent melting. And congruent melting is typically associated with special compositions that give, for example, line compounds. So if I have pure A, then at this point it goes from liquid into A without crossing through a phase boundary. But otherwise, we always have a two-phase region. So for example, here we have alpha and we have liquid. It's separated by that region. So this must be alpha plus liquid. Here we have beta and liquid. They're separated by a region, so that must be beta plus liquid. And here we have alpha and beta, and they're separated by this region, so this must be alpha plus beta. So a reading from this is exactly the same. Let's imagine that we pick a composition, say here. As we mix some A and B atoms together, we heat it up. At this point, it's all liquid. We cool it down. We're into the two-phase region of alpha plus liquid. We draw a horizontal, oops, I have some focus problems. We draw a horizontal line. We draw a horizontal line and then draw vertical lines where the horizontal line touches the phase boundaries. We can identify that where the alpha plus liquid and the alpha touch, that gives us the composition of the alpha. So I'm going to call this XB alpha. And where the alpha plus liquid and the liquid zones touch, that gives us the composition of the liquid. So I'm going to call that XBLIQ. And the composition that we put into the system, that is XB star. So we have the compositions now of the alpha and the liquid phase. We get the phase fractions from the inverse lever rule. The fraction of alpha is equal to this part, which is away from the alpha, divided by the total. So that's going to be XBLIQ minus XB star divided by XBLIQ minus XB alpha, using the inverse lever rule. And then the fraction, that's liquid, is equal to 1 minus F alpha. If we imagine what these look like in a microscope, at this region here is all liquid. At this region here is going to be liquid with some alpha precipitates that are forming little nucleus that are growing in our liquid. And now we're going to talk about the eutectic microstructure. Now, if you imagine what happens just above that phase boundary, again, focus problems, just above that phase boundary, well, just above that phase boundary, what we have is we have something that looks like alpha and liquid. And you say, well, how much? Well, if we look at it, it looks as though we're about maybe 75% alpha and about 25% liquid. And that's just kind of eyeballing it, estimating what the phase fraction is. You can actually solve it by going in and putting in the numbers, but roughly 75% alpha and 25% liquid. The minute we drop below that phase boundary, we now are in the region with alpha plus liquid. And just below that, it looks like this. We have our alpha elements, which we had over here, but now that liquid has transformed. There's no more liquid. Alpha plus liquid, and we're going to have something that looks like this type of striping. There's a couple different morphologies that you can get, but they all generally look like some type of layered stacking sequence. And what we have is we have alpha and beta that are stacked next to each other, one on top of each other. This type of stacking, this lathe structure, that's called a eutectic microstructure. It's not a eutectic phase. The only phases are alpha and beta. But the way that we arrange those are giving us the microstructure, and this type of sequence we call a eutectic microstructure. And again, once we're below that, we can figure out how much beta phase is present. Right? So we could do something, for example, drawing a horizontal line through our point where the horizontal line touches the boundaries. We draw a vertical line, sorry. So now that green arrow, that represents the composition of the alpha, and that green arrow represents the composition of the beta phase. And we know that because that's where the horizontal lines touch the phase boundaries, and we draw them down. Kind of interesting because the alpha phase has changed a little bit in composition, but now we have this beta phase, which is fairly different from the liquid, right? Because just above that melting temperature, just above that eutectic temperature, we have a liquid which has composition right here. And now the beta has composition over there. And what's happened is this beta is B atom rich, and we get a eutectic microstructure with alpha and beta. The beta is B rich, and the alpha is A rich. So we're getting a segregation of the A atoms and the B atoms into alpha and beta compositions, or the alpha and beta phases. So that's how we think about a eutectic phase diagram. It's worth noting that at any point, someone says to you, okay, so you've got alpha phase and liquid phase, what's the overall composition? The overall composition, regardless of what the microstructure is always the original composition. We don't change the composition overall, we just rearrange where the A atoms and B atoms are sitting geographically, right? So we're basically creating regions of A-rich and B-rich structures. And this has to do with crystals and crystal structures, and we'll talk about that later in class. So this is the basics of reading a binary phase diagram.